This spider built a catapult for ants. The strange part is not the launch. The ant pulls the trigger itself, using its own jaws. In a rainforest on Queensland's Cape York Peninsula, a tiny nocturnal spider hangs above the busy trails of aggressive green tree ants. Researchers call it the ballista spider, after an ancient siege engine. It belongs to the genus Proposteer, but its formal species name is still being worked out. Most spiders avoid ants. Ants bite, defend themselves chemically, recruit backup, and turn one small hunting mistake into an extremely organized workplace incident. This spider specializes in just one target, the green tree ant, Echophila smaragdina. One dangerous customer, one custom-built delivery system, and apparently no backup plan. During the day, the spider hides inside a silk retreat beneath a leaf. After dark, it descends more than half a meter toward an active ant root. Then construction begins. The spider stretches silk between a lower anchor and its main web, returning again and again with remarkable precision in total darkness. Over as long as 4 hours, it builds a vertical fan of roughly 15 to 60 tensioned silk lines, all aimed toward one small contact point. Near the anchor, those lines converge into a tiny cone. The stretched silk stores elastic energy, like dozens of loaded springs sharing the same release mechanism. The spider adds a thinner silk wrapping around the cone, retreats upward, and waits. Researchers suspect that final layer may carry an ant-attracting chemical signal. That chemical lure is not confirmed. What infrared and high-speed cameras captured next, however, is very real and extremely inconvenient for the ant. A worker ant approaches the cone and attacks it, exactly as territorial green tree ants often attack unfamiliar material. When it bites, the cone detaches. The released bundle contracts almost instantly, overcoming the ant's grip, pulling it away from the surface and launching it into the main web above. High-speed recordings measured accelerations up to about 1,367 meters per second squared, roughly 140 times Earth's gravity. The ant can travel more than 30 centimeters upward in a fraction of a second. At that scale, this is not a jump. It is an unscheduled flight. This solves a major engineering problem. Green tree ants have adhesive footpads, chemical defenses, and nearby nestmates ready to respond rapidly to alarm signals. The trap must defeat the ant's grip, remove it from the trail immediately, and stop reinforcements from turning dinner into a very hostile committee meeting. The spider does not rush toward the struggling ant. It waits until the prey is fully entangled, then approaches safely and wraps it in additional silk. Researchers spent 10 days and nights documenting the behavior with infrared and high-speed cameras, then carried silk samples to Germany for microscopic and mechanical analysis. Scanning electron microscopy revealed the silk structure, while physical tests measured how much energy the tensioned bundle stored and how quickly that energy was released. Those tests showed the snare is not merely fast. Relative to its mass, it has higher energy and power performance than other known silk-powered biological catapults. Normalized to 1 kilogram of silk, the system could store about 78 kilojoules and briefly produce nearly 12 megawatts of power during release. The actual web weighs nowhere near 1 kilogram. That normalized comparison simply reveals how concentrated the energy release becomes when measured at spider scale. Here is the second major reveal. The spider does not sense the ant and fire the weapon. The prey activates the entire mechanism by biting it. The ant is the target, the trigger, and very briefly, the projectile. Nature has merged user input, express delivery, and complaint handling into one automated system. Patch would classify this as customer service, except the customer presses the button with its face and leaves the premises at 140 G. Researchers think extreme specialization drove this design. A general-purpose web might fail against ants that cling tightly, defend themselves, and summon hundreds of nearby workers. A dedicated trap exploits one predictable reaction. Green tree ants aggressively bite the unfamiliar silk cone placed directly along their established foraging route. But the suspected pheromone remains a hypothesis, and researchers have not yet demonstrated exactly which chemical attracts the ants or how narrowly prey-specific the trap is. The confirmed discovery is already strange enough. A spider builds a high-powered spring, gives its prey access to the trigger, and patiently waits above it. If evolution built this much engineering for one ant species, what other tiny machines are still operating above our heads without instructions, labels, or a user manual?